IP version 6 fundamentals. Now this is really an interesting topic because we are migrating to this version and it is happening day by day. The improvement happens everywhere, the migration from 4 to 6. So it's an interesting topic, the current topic, hot topic we can say. First thing, we will discuss the difference between 4 and 6. In what way 6 is better than 4. We'll see the difference. Next, what is extension header? In what way that is an added advantage? How the addressing architecture in IPv6 looks, and what is ICMP version 6. Neighbor discovery happens in IPv6, which is not in IPv4. In IPv4, neighbor discovery happens layer 2 level when an ARP request is sent, ARP address or MAC address is learned through ARP request and response. A kind of layer 2 discovery happens. So that is a kind of layer 2 and layer 3 neighbor discovery in IPv4. In IPv6, we got neighbor discovery using a link local address. We will discuss about that. This discovery happens through this protocol called ICMP version 6. And we also have something called auto configuration. Means, there are various auto configurations in IPv6. One is general. Auto configuration means the link local address is automatically configured. The interface portion of the address is automatically configured. Now, moreover, apart from this, there is another auto configuration, that is automatic IP address configuration. Even the IP address is configured, the complete IP address including the network portion and the host portion is automatically configured. So that also we will discuss today, and then how to configure IPv6 in a Cisco iOS router. So these are the topics for our today's discussion. So let's start with the first one. First one, the difference between IPv4 and IPv6. Now, when you say the difference, the major difference is this: the address space. The address space is really very big. IPv6 address space is very, very big. Now, the size of IPv4 is just 32-bit. 32-bit only. Millions of IP addresses come out of this. Just 32-bit. Now, if I add 1 bit to this, for example, if I have 2 million address, if I make it as 33-bit, I'm going to get 4 million address. Just 1 bit if I add to this, always the binary doubles. Example, I got 3 bits. The binary value, this, the binary to decimal value, 1, 2, 4, the value is 7. 4 plus 2 plus 1. Now if I add just 1 bit to this, here the face value will be 8 because it is 2 to the power of 3. Here 2 to the power of 2, 2 to the power of 1 and 2 to the power of 0. So 2 to the power of 3 is 8. 8 plus 4 plus 2 plus 1 is just doubled. What is that? 15. Before adding this, I was having 7. After adding this, I got double the number. So adding 1 bit might have solved the problem. What problem? The running out of IP address. We were not having sufficient IPv4 address. So that might have solved just by adding 1 bit, but it is not just added 1 bit. No, they have added really too many bits. IANA has designed this by keeping the future in mind. So later, they don't want any down the line scarcity of IP address. So you got 128 bit, very, very big. So that's the first difference, the addressing size. It's a very big size. Now how big? 128 bit. How big? How many IP address I can get out of it? It's really a very big number. I'll write it for you.
3, 4, 0, 2, 8, 2, 3, 6, 6, 9, 2, 0, 9, 3, 8, 4, 6, 3. Again 4, 6, 3, 3, 7, 4, 6, 0, 7, 4, 3, 1, 7, 6, 8, 2, 1, 1, 4, 5, 6. I don't know how to name this. These many number of IP address you will get. I don't remember this number. I wrote it before the class. I referred some document. I wrote it on the paper. I'm just writing from referring the paper. This big is the IPv6 address. It can give you this many IP address. You need not to remember this number. All that you need to say is, if someone is asking how many IP address we will get, 2 to the power of 128. That's a smart answer. 2 to the power of 128. Number of addresses, number of nodes we get out of this. Alright, now next thing is about security. The design of IPv6 is designed in the way that it adapts so easily to IPsec kind of security. So if you talk about security VPNs, IPsec is the hero there. IPsec is the protocol that makes the security VPN happen. So IPsec by default, the IPv6 header adapts. In IPv4, we need to do a lot of additional encapsulation to make IPsec to work with IPv4. But in IPv6, yes. Yeah. Next is NATing. Network address translation. Do we need NATing? Not really for translation from a local address to a... Not really for translation between inside address to inside local address to inside global address, or in another word, not for end-to-end communication. I need to do translation as we do in IPv4. In IPv4 we do translation for end-to-end communication, meaning I do not want to show my private IP address. So what I do, I translate from private IP address to public IP address so that the other end will see that this is coming from so and so public IP address. So that's for end-to-end communication. We do NATing in IPv4. That type of NATing we don't do in IPv6. The reason is we don't have any private scheme of address. We have all the address as global unique cached address, global unique address. It is all going to be public. Every node in IPv6 network is a public node. No private and public. In IPv4 we got private node, we got public node, so we translate from private to public in order to reach the other network in public. So that type of end-to-end communication, NATing we don't do in IPv6, but still we do NATing. That NATing we called as NATPT, NAT protocol translation, where we got our local network in IPv6 and our remote office is also in IPv6, or maybe in IPv6 or in IPv4, and in the middle the internet cloud is in IPv4. So when you have IPv4 in the middle, you cannot route the IPv6 packet over the IPv4. For that, what we do is we translate IPv6 to IPv4, and when the return packet comes, we translate IPv4 back to IPv6. So that type of translation we do, and we call that also as a NAT in IPv6. That is not for end-to-end communication. That is to solve the problem which we will be having during the migration period. So Do we have NAT in IPv6? No. Next is the administrative workload. If you talk about the header, this IPv6 has got a simplified header, meaning the header don't have unnecessary field. The header has a reasonable number of fields which is really needed for routing, which is frequently used during the routing process. If there is an additional need for a field, that field will be added then and there whenever it is needed. That we call it as extension header. So our processing is more efficient when we do extension header approach. IPv6 has got an extension header approach. Whenever you need some additional field, that field get added to your IP header. It's not like a normal IPv4 header. In IPv4 header, you got lot of fields always being processed, though it has got something to do or not. There are a lot of fields, even though it is not in use, it gets processed on every device, which brings down the efficiency. But in IPv6 we got a simplified header which makes the routing process, administrative workload process more scalable and more efficient. So extension header approaches we have in IPv6. Next, mobile device support. This is not needed for us, but still, I want you to have an idea of what it is. Mobile device support, meaning when I move my node from one network to another network, when I move my PC or any IPv6 device from one network to the another network, I got a seamless switch over. Seamless switch over, meaning what? The user don't experience that he is jumping between one network to the another network. A seamless switch over happens between one network to another network. Those things are taken care by the mobile IP address version 6. So that is there in IPv6, but in IPv4 it is not like that. When you move your mobile device, IPv4 device, from one network to another network, there is a lot of registration needed, learning needed. When you switch from one network to another network, the interface to which you connect to a new network, that has to learn, and definitely the user will come across the downtime. We don't have that such downtime, or a user never experienced that he is switching to another network. It is happening seamlessly, and those things are taken care by MIP version 6 protocol. MIP version 6. Alright, the next is the IPv6 header. If you see the IPv6 header, let's say the size, now you got source IPv6, source IP version 6, IP version 6 address, and destination IPv6 address, and we got the payload length, field. We got the information about the next header, and we got a hop limit field, and we got version, we got traffic class, and then at last we got flow label. So these are the fields that we do have on IPv6 header.
Now version 4, for marking version, how many bits are being used? For marking the version is always 6 because it's an IPv6 header. For that you got 4-bit reservation for that. And for the traffic class, what is traffic class? The quality of service. TOS bytes. It is same like your IPv4. In IPv4 we got 8-bit reservation for that. It's the same number of bit we got reserved in IPv6 as well. And for flow label, we got 20-bit reservation. And for payload length, we got 16-bit reservation. And for the next header, payload and the next header, for next header marking, the next header identification number, to mark that the header, the protocol which is going to follow. Now to do that we got 8 bits reservation. And for the next hop limit marking, like TTL function, we call it as TTL value in IPv4. Here we call it as hop limit. For that we got 8-bit. And then for the source IPv6 address, as we already know, it's a 128-bit address. So for source IPv6 address you got 128-bit, and for the destination IPv6 address we got 128 bits. So this is the this is how the IPv6 header is designed. Simplified header. You don't have too many fields. If you just see the IPv4 address, IPv4 header, you can just Google and see the image. You will have too many fields like protocol and so on. Though you may not have any routing protocol running, but still the field will be there with some garbages getting processed on every hop. But here, whenever you need something, that is getting added as an extension. So let's see something about extension. You already got IPv6. Okay, the topic is extension header. So you already got an IPv6 header, which we just now saw. IPv6 header. To this, what we have is we have TCP header plus data as the extension. Now if you need some authentication, then what happens is, to your IPv6 header, the authentication header is getting added. Authentication header. And followed by your TCP header plus data. And this also will have the next header marking, which is TCP header marking, the next TCP header marking. Now if I need very strong authentication like ESP, which if you are a security student, you may be aware of ESP, 3 days and so on, then we will have one more field. You will have IPv6 field, you will have authentication header field, but here TCP is not the authentication header, here ESP is the header. So you got again another ESP header here,
which is mapping to TCP, and the default TCP header with the data. So this is just an example. Whatever the type of authentication, here authentication is ESP and TCP. Here the TCP itself is acting supporting authentication here. So like this, the header is getting extended as we keep adding more and more services whenever you need. Now what is the advantage here? You got a simplified header. Because you don't do authentication, you don't have this field. If you don't have this field, less time is taken to process. So routing happens very faster. Even though your IPv6 address is bigger than IPv4 address, IPv6 header get processed faster than IPv4 header because of this extension header approach. Just I gave an example how the extension header works. Now, in the header there is a field number. Like there is something called hop to hop option. For that the field number is 0. Hop by hop option. Not really necessary these things, just I'm giving you an idea. So this one has got field number 0 has got information about the path that needs to be examined by every node or every hop that process the packet. That is field number 0. Field number 43 will have routing information. This is where the protocol MIP version 6 is used. Mobile IP address. Mobile IP version 6, which gives you the seamless switching between network for mobility. In IPv6 actually fragmentation is not necessary. Why fragment is not necessary? Because how it works is, in IPv4 fragmentation happens. You cut the packet segments into small segments, you fragment and send it. Whereas here in IPv6 it doesn't work like that. It will check the MTU maximum transmission unit on every source to destination. In between every source to destination, it will check the MTU value. Based on the MTU value, it is going to structure the packet. So there is no fragmenting concept. Fragmenting concept will come only when your packet size is very big but MTU size is very low on the interface on the router. You need to fragment this so that it will fit in here. Whereas in IPv6 you don't have the problem. The reason is it dynamically discovers the MTU size on the path. We'll talk about the MTU discovery in some time. Just I want to make a point here. Fragmentation is not necessary. So those information about fragmentation means it has to discover the size of MTU. So those informations, the MTU values on the path, those are stored in field number 44. Authentication header, field number 51. And then if you want to have ESP, this is the value. Authentication header number is 51, and ESP 50 is for ESP, encapsulation security payload. That's the protocol number. For ESP it is 50, for authentication it is 51. So this is to provide the difference between this is very important for security, guys. In IPsec VPN we go with AH or ESP. AH only provides integrity and authentication, whereas ESP provides integrity, authentication and confidentiality. All these three. So ESP is more good and stronger in providing security than AH. In AH you got only authentication and integrity, there is no confidentiality. When we learn VPN, we will go in very deep manner here about this. So those two protocols are very important when we talk about IPsec VPN. Now next is the addressing architecture. Addressing architecture in IPv6. Let me quickly make this bigger. So the addressing architecture, as we already know, the size of IPv6 address is 128. Now 128 what? 128 bit. Remembering this 128 is very, very difficult. So what is done is, instead of having it as in a binary number, instead of having it as a bit, we got it as a hexadecimal representation. Hexadecimal representation. So we know about hexadecimal. When you say binary, you say 2. That's the reason, when I have 3 bits of binary, I got 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Because it is binary, meaning I got only 0 and 1, 2 numbers. So I put 2 to the power of 0, which is 1 here, 2 here, 4 here. Assume I got hexa, 3 hexa. Then what it means is 16 to the power of 0. 16 to the power of 1, 16 to the power of 2. This is what it means. 16 to the power of 3. This is how we will have a very big number. But I don't want to have this approach. This approach is not really a good approach. I'll give you another approach. We'll talk about binary and hexa. Now to write 16 in binary, how many bits I need? 1, 2, 3, 4 bits. 4 bit is equal to 1 hexabit. 1 hexabit is 16. 2 to the power of 4 is 2 into 2 into 2 into 2. 2 to the 4, 4 to the 8, 8 to the 16. 2 to the 4, 4 to the 8, 8 to the 16. So 4 bit is equal to 1 bit in hexa. Now if I write 1, 2, 3, 4, I got here 4 bit, 4 bit of binary, 4 bit of binary, 4 bit of binary. So 4, 4, 4, 4, it is 16 bit. 16 bit. Likewise, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 4, no, one more, 1, 2, 3, 4. Now you got 8 sets of 1, 2, 3, 4. Meaning, if each is 16 bit, 16 8s are 128. That's the size of our IPv6 address. So IPv6 address, for our easy manipulation, easy handling, that 128 bit is being divided into 8 hexa decimal group. Each group value is 16. Here you got 4 bit, because it is, why I have got 4 bit, because in binary 4 bit is equal to 16. I need 4 bit to write in binary. So when you talk about binary, when you talk about bits, this is how it works. 4 bit, 4 bit, 4 bit, 4 bit. Totally 16 bits I got here. Why 4 bit? The maximum number, the biggest number is 16. To write 16 in binary, you need 4. Because it is 128 bit, I calculate in bits. Hexadecimal maximum is 16. The F needs 4 bit to write. To write F, you need 4 bit binary value. 4 bits of binary. Only then you can write the biggest number in the hexa. Alright, so this is how the address has been structured. We got 8 groups. See, this is very important. 1, 2, 3, 4, 5, 6, 7, 8 groups of 16 bits, which is equal to 128. But if it is in binary, then I need to write 128 dots. I have not written 128 dots here. I have written just 32 dots. Only 32 dots. Even if I write IPv4 address, I write only 32 dot. Only the difference is I put dot here after every 8 bits. Same thing I have written here. 4, 4, 4, 4, 4, 4, 4. 32 dots only I have drawn. Same 32 dots which I write for IPv4. But the difference is here 1 dot is equal to 1 bit, but here 1 dot equal to 4 bits. And the separation is after every 4 hexa bits. After every 4 hexa bits, we got a colon, semicolon. You got IPv6 address 1, 2, 3, 4, 5, 6. I think I didn't draw one more. This is IPv4 address in bits. When I just put dots after every 4, then I make it as IPv6. So let's see an example. This can go from 0 to F. 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. After 9 comes A, B, C, D, E, F. Because it is hexa. 0 to F. So if you see the example, I can write like this: 2001 colon. This is 2. Meaning if I need to write it in binary, then it is like this: 0010, because each bit is 4 bit, 1, 2, 3, 4. And here 0 means here 0, so here also 0, which means 0, 0, 0, 0. That's this 0. And this 0 is 0, 0, 0, 0. And this 1 is 0, 0, 0, 1. So just one hectade can be written like this: 2001 colon. Now let me write the second one. Second one, all zeros. Meaning how many zeros? 16 zeros. I am writing 4. Each 0 is 40, equivalent to 40. See how very difficult it is to write binary. That's why we are asked to do hexa. IPv6 is represented in hexa. Okay, now let me finish writing the example. I don't want this. So it is 2000 colon 2000 or 2001, whatever, colon 0000 colon 0000 colon ABCD colon 010C colon CDEF colon 2345, something randomly I'm writing 1234. Okay, 1223. See, this is how the IPv6 address will look like. But okay, one more thing. This is case insensitive. So you can use uppercase or lowercase, no problem. You can use any case. Case insensitive. You can also have mixed case, no problem. Next is leading zero. Leading zero in a field is an optional. Meaning when you write, you need not to write this 0. See, 010C. It is equal to 10C. So you can avoid this 0 if you want while writing. But don't remove this 0. If you remove this 0, the value will change. 2000 will become 2. But leading 0, if you remove, the value will not change. So leading 0 is optional. Next is successive fields of 0 or consecutive zeros. Successive fields of 0 are represented as just colon colon. But, very important, but only once in an address. Meaning either this or this, I can put colon colon. Sorry. Either this or, let's assume we got 0000 here also. All these are zeros. All these 3 are zeros and these 2 are 0. Either this I can write like this or this. Instead of writing these, I can just put colon. Only once, either you do here or here. So I can write like this, 2000 colon, all leading zeros I'll cut off, I'll just put 10. All leading 0 I'll cut off, I'll just put 10. Say I am not doing this successive fields of 0. Consecutive 0, I'm not writing like this. I'm not writing here, I'm not using it here. ABCD, because this has got more 0, I'm just putting like this 1 2 2 3. That's it. How small the address is now. Instead of writing these many zeros, I just put colon. I should not do it here also. Only once you can do in an address. So now what will happen if I assign this IP address to an interface on a router? Router knows that there need to be 8 group of hexadecimal hectates. 1 is here, 2 is here, 3, 4, 5 is here. So remaining 6, 7, 8, 3 field. 3 sets of 0 will be added here automatically. See, 3 sets of 0 exactly. In case if I do on both places, then confusion. Should I add 3 sets of 0 here, 2 sets of 0 here, or 2 set here, 3 set here, or 1 set here and 4 set here? Confusion. 4 here, 1 set, confusion. To avoid that confusion, you can remove the consecutive zeros and put colon only once to shrink the size of the IPv6 address. Let's talk about address architecture. Address architecture. See, when you talk about IPv6 address, there are three major group of address we can say. In IPv4, we used to say unicast, multicast, broadcast. Even anycast is seen in IPv4, but it's not much popular. In here, in IPv6, we don't have broadcast. We got unicast, we got multicast, we got anycast. Now, when you talk about unicast, there are various types of address we got unicast. One, just colon. This is also equal to 0 colon 0 colon 0 colon 0 colon 0 colon 0 colon 0. All bits are 0. 128 bits are 0. Instead of writing this many zeros, just now we saw, you can write what? Colon. Only once. Anyway, this address is totally 0, so only once I put. This address is also unicast address, and it is called as unspecified address. This is just, if you put colon, it is unspecified unicast address. Unspecified unicast address. A kind of what? Default address. When you write a default route, we used to say 0.0.0.0, which means any. That's what unspecified, any address. Instead of writing 0.0.0.0 in IPv4, you just write dot. It's not possible in IPv4, but in IPv6, instead of saying any network, putting 000, you can put just colon. Next is just colon 1. This is equal to what? 0 colon 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 1. 8 sets of number. So we got all the higher order bits 0 except the first lower order bit, the last lower order bit. Only one bit is turned on. That's the last bit. Colon 1. This is the loopback unicast address. Loop back address. You remember in IPv4, we got 127.0.0.1 till 127.255.255.255. These many address, thousands of addresses wasted just to do loopback verification. That wastage is not happening in IPv6. Only one specific address defined as a loopback address, and it is just colon 1. After, there is other two addresses, very important. One, the address that starts with FE80. This address is also a unicast address. It is called as link local address. What's the purpose of this address? It is to discover neighbor. For neighbor discovery, this address is used. And next is the unicast. What to say? Unicast address. The other unicast address is the global unicast address. The global unicast address. The one which always starts with 2000, 2001, 2002. Global unicast address. Next is next type of address we have is the multicast address. Okay, multicast address. These are all come under what? Unicast address. So multicast address always starts with FF02. The multicast address will always start with FF02. So if you talk about OSPF multicast address, in IPv6 the OSPF multicast address is FF02::5 and 6. Multicast address for all nodes FF02::1. This is the multicast address for all nodes. FF02::2. It's a multicast address for all routers. Likewise, we have got many. FF02::9, which is IPv6 EIGRP. Likewise, 10. I think I'm saying opposite. FF02::9 is RAPE. FF02::10 is EIGRP, IPv6 EIGRP. IPv6 RAPE, this one. FF02::10 is IPv6 EIGRP. So always multicast address starts with FF02. Next comes anycast address. Anycast. What is the anycast means? One to the closest, one to the nearest. This is mainly used in mobile IP address, mobile IPv6 address, and for the DNS discovery. DNS discovery and mobile IP address, IPv6 home agent discovery, that's how they call it as. So anycast address. These are the different types of address schemes we got. Anycast address, you can use any address and define it as an anycast address. Alright, so next is about the again, still in the architecture. If you talk about the forum or the organization that is responsible for providing IP address is IANA. IANA is an organization which is responsible for providing IP address. Now this IANA has divided the IP address into 5 different levels. This IPv6 address they have defined in 5 different levels. One, IANA first level, what they say is this 2000, you may have a very big address. In that big address, the first hectate, the 16-bit, the first 16-bit is called as ARIN. ARIN. What does that ARIN stands for? The American Registry for Internet Number. American Registry for Internet Number. The first 2 hectares, like 2000:0001:, slash 24. I'm sorry, then I shouldn't put 1 here. Okay. The 24 bits, the first 24 bit. This is actually 16, this is actually 16, then it is 32. I'm not talking about all the bits here. From here only this bit is taken. So total is 24. The 24, they call it as top level aggregator ID. TLAID. Top level aggregator ID. This is how they have named this bits. Top level aggregator ID. Next they call it as next level aggregator ID. What is next level aggregator ID? First 48 bit. Because that first 48 bit talks about what network you are in. Like 2000 colon 0000 colon 0001 colon 48. So here 16, 16, 16. 16, 16, 16, 48 bit. So this 48 bit is called as NLA, next level aggregator. So not network level, next level aggregator. Next level aggregator. And then for SLA, what is SLA stands for? SLA stands for site level aggregation, which talks about the entire network portion. This is still not network portion over. In IPv6, you got 128 bit. So first 64 bit really talks about network along with subnetting. The last 64 bit talks about the host ID. But here we call it as interface ID. The last 64 bit in 128 we call it as interface ID. Instead of calling host ID to identify the computer, we need the last 64. The first 64 is to identify the network, but we don't call it as network ID. We call it as global ID, global prefix or global ID, network ID. Instead of calling network ID, we call it as global ID, GLOBAL, global ID. So that is what called as SLA. Site level aggregation, like 2000 colon 0000 colon 0001 colon 1234 colon slash 64. At last the interface IP address. Yeah, what is the interface IP address? The entire thing. The SLA plus SLA is 2000 colon 0000 colon 0001 colon 1234. This talks about the network. So the remaining portions when I have, then it is called interface ID, which I assign to an interface like colon 1, meaning all 64 bit except this one, except the 64th bit, all are 0. So I put colon 1, which is an interface ID. So this is how the namings have been given for the architecture of IPv6 address. So let me draw the same thing in a diagram so that you can better understand this. See, we got higher order 3 bits. Now that will be a confusion diagram. This is better, not necessary. Okay, so next is about the EUI64. There is a concept called EUI64. Still we are in addressing, IP addressing architecture. There is something called extended unique identifier 64, meaning Interface identifier can be stateless auto-configured. Interface identifier. What is interface identifier? If you take 128-bit IPv6 address, first 64-bit is global identifier, network, which talks about network. That is not interface identifier. This 64, the second 64 is the interface identifier. So you need not to assign the interface identifier. It can be dynamically assigned. Only this portion you assign. This portion will be dynamically assigned by using your MAC address. That is what called as enhanced unique identifier, EUI. You can also technically say like this: interface identifier for stateless auto configuration. Automatically address has been configured. Which address? Interface identifier is configured, and it is not stateful, it is stateless. What is stateless and stateful? Stateful means you know what you are typing statically. Stateless means dynamically. You don't know what has been assigned, but it is assigned. There is no record of what has been assigned. You don't have in your document, but some address is assigned. That is stateless. So interface ID can be dynamically assigned. You no need to assign, but if you want to assign, you can definitely assign it. The complete IP address, 128-bit address, you can assign it. But if you want your interface identification 64-bit to be determined by your router or a computer, you can definitely allow it to do it. You can make use of it, auto configuration. That what it will do is it will take the MAC address. Let's say your MAC address is 001C ABCD 6432. What it will do, it's a 48-bit address, but what you need is 64-bit. So this MAC address, it will remove the vendor portion separate. It will take the vendor portion. What is vendor portion? 001C AB. That is the vendor portion. And it will also take this one out, node portion. This is the node portion. It will take the node portion separate. CD 6432. Now totally 48-bit MAC address is being deployed, but you need 64-bit. So what it does is it will add 16-bit. So 48 plus 16 is 64. So what is that 16-bit that is added here? FE. This is the only 16-bit always added. Always, it's a standard. It will take the MAC address and it will add this value, 16-bit value, to extend it. That's why we call it as extended unique identifier. MAC address is a unique identifier. You take this unique identifier and you extend it by adding the MAC address. Now you got what? A unique IP address. Why it is unique? Because it is taken out of MAC address. MAC address is unique on every interface. If MAC address is unique, then this derived EUI64 is also a unique address. So there won't be a conflict, though the IP address is assigned dynamically, though the interface portion has been taken dynamically. Because it is taken from MAC address, it is going to be unique. It will never conflict with other device. Right. Next is
how this, the neighbor discovery happens. The neighbor discovery, see, if I have one router, let's say 10.0.0.1 IPv4 address, 10.0.0.2. When we have something like this, after assigning IP address, this is on, you say no shutdown. Now when you go here and ping 10.0.0.2, definitely the first packet you will lose. Second packet onwards you will ping. Why, when you try pinging, then and there only then, when you try pinging, what packet is trying to go? ICMP. But this router, to reach 10.0.0.2, it needs to know the MAC address of 10.0.0.2. Let's say 10.0.0.2 MAC address is BBB and this is AAA. Now router 1 should know the MAC address of 10.0.0.2. Only then this layer 2 information will be full. The layer 2 information will be there on the IP header. So what happens is, it sends the ARP request and wait for the response. ARP response come from a B, you get the ARP response. Meanwhile, one ICMP packet is already dropped. But in IPv6, the story is different. When we have two routers, and in here let's say 2001:1/64. What it means is, this is 128-bit address. In 128-bit address, first 64 is a network. 2001:2/64. Now what happens is, when I go in and ping here, right from the very first packet I get the success. How it is possible? It is possible because R1, before your ping starts, it has already discovered R2. Now this discovery is by using the protocol called ICMP version 6. ICMP version 6, what it does is, it will use the link local address. See, for every link, there will be address called link local address, always start with FE80. You no need to assign this address. If you want to assign, you can assign. This address is dynamically generated, same like as we discussed, by using the MAC address. But the first octet will be always FE80. Let's assume I have assigned manually. You can also assign manually. FE80::2. I assign manually. Now the moment this address comes dynamically or manually, R1 will go and say, hey, my name is FE80::1. Is there anyone there to object this? If anyone is having the same thing, you can object now. So it sends that information. Now this we called as NS, neighbor solicitation, NS. In neighbor discovery, neighbor solicitation. This guy will say, my name is FE80::2. This is my link local address. What do you say? Is there anyone objecting? Now if no one is objecting, then there is no DAD. What is DAD? Duplicate address detection. So R1 will say, okay, I'm fixing with this. This is my link local address. R2 will say, okay, I'm fixing with this. And I also make a note of your address. Okay, you are R1 and your address is FE80::1.
How it knows, how R2 knows? Because this one was soliciting, this one was sending. Router solicitation, RS. We'll talk about RS in some time. No, neighbor solicitation is what we are talking about. Neighbor solicitation is nothing but sending the link local address. When this link local address came to R2, R2 has registered it. Likewise, when this link local address come, R1 will register. Okay, R2's link local address is FE80::2. So they discover beforehand, before you ping, through neighbor solicitation. After this, what happened is route solicitation. What is route solicitation? This guy says, hey, my IP address is this. This guy says, my IP address is this. Do you object? No one is objecting. Again, dad. So R1 learns the neighbor's link local address and the global address on both the side. So what happens is, each learn themselves by neighbor advertisement, by neighbor solicitation, by route solicitation, and by route advertisement. See, neighbor solicitation is initially you are sending doubtfully. Is there anyone having the same address? Once there is no one, once there is a DAD, duplicate address detection is not there, it fixes the address. It is fixing that address. This is my address. Neighbor copies that. Likewise, route solicitation happens for 2000::1. Once there is no duplication in that link, this is fixing the route address, the host address. And this is also used for auto configuration. We will talk about auto configuration after some time. Address auto configuration. What I mean when I say auto configuration, R1 you got, R2 you got. On R1 you will say IP address is 2001::1/64. On R2 you will simply say no shutdown and IPv6 auto address configuration. You will not assign any IP address. No assigning of IP address. But this will automatically assign an IP address. You know how? From this advertisement that is coming from R1, R2 will learn the network is 2001::. It learned the network portion. Now R2 will take its own MAC address, add it here by EUI64 and got a new IP address automatically configured, which is called auto configuration. So it is the same ICMP version 6 that is used to do neighbor discovery, also used for auto address configuration. I'll demonstrate this. And whenever these advertisements are sent, they are sent to TTL of 255. It is sent to TTL of 255. So whoever receives it, they learn the neighbor's address. So that's what neighbor solicitation, neighbor advertisement, route solicitation, router advertisement, duplicate address detection, DAD, and auto address configuration, all the stuff. So this is where we are going to stop for the day. And as I gave you in the introduction, we will be seeing IPv4 to 6 differences. We saw that IPv6 header and extension header, we saw that address architecture, we saw ICMP version 6, we saw the neighbor discovery, we saw the auto address configuration, iOS configuration, along with the detailed thing that whatever we studied, including auto address configuration, I'll demonstrate it in the next class along with the iOS configuration. So if you have any doubt, you can ask me now.